Hi, everyone. I think it's 4 o'clock, or at least where I am, it's 4 o'clock. So we'll go ahead and get started. Welcome to the first Landscapes Live talk of this fall's series. I'm Charlie Shobe. I'm one of the members of the Landscapes Live organizing committee. The others are Steffi Tofelde, who will be helping out chairing today's seminar, as well as Philippe Stier, Vivi Peterson, Pierre Vallat, and Wolfgang Schwanghart. And as you can see on the screen in front of you, we've got a really fantastic lineup of talks coming up for the next couple of months or so. So definitely stay tuned for those, always at this time on Thursday. So without further ado, I will go ahead and stop sharing here and introduce our first speaker of the fall. We're really excited to have John Armitage here today. And John has quite an extensive CV, it turns out, upon our conversation before the talk. After doing his PhD at Southampton, the National Oceanography Center, went to Imperial College for a postdoc, won a Marie Curie fellowship to work at IPGP in Paris, then back to Royal Holloway University in London, IPGP again, and is now at the IFP Energy Nouvelle in France. So we're really excited to have John here today talking about reproducible landscapes and just a couple of things about how the talk will go. John will give his talk. Near the end of the talk, we'll open up the chat box for questions. So you're welcome to type those in when the time comes, or you can raise your hand and then that'll enable you to turn on your camera and ask a question. So I will go ahead and turn it over to John. Thanks so much.
Okay, I'm going to share my screen then. Okay, so I see there's 77 of you. It's a bit weird giving a presentation to all of you in separate rooms. It's kind of more like I'm talking to you individually. The talk, well, I went on a little adventure recently. So like Charlie said, I did a postdoc at IPGP, Institut de Physique de Globe de Paris, and that ended at about September last year. And then I decided to go into the private sector. Had a little bit of fun trying to make a startup, and then I joined the startup, and then I got involved in continuous integration and Docker containers and Kubernetes. And then I left all of that and went back to more kind of academic research, but in a strange organization called IFP Energy Nouvelle. IFP stands for Institut Français de Pétrole, but we don't do petrol so much anymore unless Total gives us money. What we do is we use government money to look at renewable energy and try and work on sustainability and climate change. And it's sort of related, this presentation, not totally, but it's a subject that's close to my heart. It's reproducible and it's on landscapes. And I'll just kick off and start talking. This presentation will go in two parts. I'm going to do part one, that's some research into flow routing. Because I left academia, this comes from last year. I have presented this before, so if you've seen it before, you can go make a cup of coffee and chill out. And then in part two, I'm going to try and go through some steps, let's say, to make it reproducible. I'll move this little black box to somewhere less annoying. And many years ago, when I was doing research into the composition, major element oxide composition of lavas when they are erupted at volcanic margins, I gave a presentation where I found the lovely phrase by Professor Box, he's a statistician. He said that all models are wrong, but some are useful. And I thought I would add it, that all models are wrong, some are useful, but only if they're reproducible. So the part one. Right. There's lots of landscape evolution models out there now. In GFZ, there's Fastscape. It's lovely code. It's probably reproducible. It's certainly in a GitHub repository, and Benoit is doing a lovely job getting it running. There's other landscape evolution models like Badlands, MyBadlands in Python if you prefer, or LandLab. And in all of these landscape evolution models, I think a dirty little secret is that the results are resolution dependent. That is, the resolution of your input digital elevation model will impact the results. And I think the source of this resolution dependence is how runoff or precipitation is routed down the model surface. And in two papers, one by Pelletier and the other by Jeroen Schroer, they've shown that if you use a multiple flow direction routing algorithm, then you get a different output or a different outcome for your landscape if you use a single flow direction routing algorithm. So here is two measures that I think should be resolution independent for a landscape evolution model. Sediment flux out definitely shouldn't be a function of the model resolution. And the wavelengths of valley spacing shouldn't be a function of model resolution, model revolution. And this is what I mean by it. Here's a little landscape evolution model. I'll just pull him up, rotate him around. This is the output after, I don't know, some time. And we've got valleys. And what I want is that the valley spacing is not a function of my grid resolution. And the sediment flux out of that model is not a function of that grid resolution. Well, how big should a grid be? What am I solving? So the first question I had in my head last year, perhaps 2 years ago, was how wide are rivers? And there's a nice data set by Allen and Baldesky published, I think, in Science in 2018. If you go to the GitHub repository and click on that link, you'll find it. And in that, they gave their data. That's lovely, nice and reproducible. And you can plot the mean river width and the frequency. And you can find, if I'll increase the number of bins for you if you want, that most rivers are very narrow, at least less than 1 kilometer wide. And that creates an interesting problem when you've got a landscape evolution model that might have a grid spacing of 1 kilometer. So last year I published this paper where I looked at landscape evolution with a very simple classic model by Terence Smith and Bretherton in 1972 that says that the change in elevation is equal to the divergence of the sediment flux, that's this term here, plus uplift. And that if sediment flux is equal to some linear function of slope and some water accumulation to raise to the power of n is greater than 1 to make a concentrative flow, and c a coefficient. And this can be solved. I wrote a simple code in Python to solve it using the library Phoenix. And we'll give you a little example of it. I saw this kind of cool landscape on Google Chrome because I have an app installed that when every time I open a new tab, it shows me a piece of landscape. So I just chose this, and we can select it in a Python script with some bounds, which is just a variable, and initialize it with a function and run the model. So this is somewhere near the Khovskol Lake in northern Mongolia. So in a Python script, you would import Phlegm, that's the model, finite Phoenix landscape evolution model, and we'd import two functions, initialize and solve, and of course, I'll need some Phoenix for plotting it. And then I take in the bounds, this is the coordinates. I'm just going to pull some SRTM data and initialize the model space and some mesh and trial solution and various other finite element bits and bobs. And then we can plot the input condition. So this is just using a function called elevation, which is available in Python, which pulls data off SRTMs, off the shuttle data. So this will be my input condition, and I run the model. So here's my physical model space. We have kappa C the exponent, and alpha. So kappa is the linear diffusion coefficient, c is the coefficient on the water flux, n is the exponent on the water flux, alpha is precipitation, and u is uplift. And so this is relatively diffusive. My diffusion coefficient is 1 meter squared per year. C has horrible units, so I'm not going to say it, but it's small. N is greater than 1, so we're going to make valleys, and we've got tiny bit of uplift. And okay, I make an output directory, and I run it. Here's the line of code to run it. I obviously ran it before I started presenting, otherwise we'd have to twiddle our thumbs for 5 minutes. And here's an output of the model. And we can plot the water flux on it. It looks more pretty. And we're left with this question: what resolution for my grid is appropriate for the landscape evolution? And is this model even resolution dependent? Here's all the water flux coming down. And so that's what I'm going to explore in the next section as I sit right on my slide deck. How to route water. I came up with 4 possibilities. We can say, I use a triangular grid, we can say that rainfall falls on my triangles and it fills up the area of the triangle and it goes down the steepest slope. It's one possibility. I should add that all the water here, what I'm making is a simple assumption that the hydraulic gradient is identical to the topographic gradient. So water cannot overcome any small barriers. So rainfall falls on the area of the cell and it goes down the steepest slope and off we go. We'll call this a cell to cell. This is one cell, steepest descent algorithm. Another idea I had, I'm not unique in these ideas though, is that water falls on the cell of a certain area. It goes down the slopes, but it goes down all slopes, weighted by the relative gradient. Then I had the idea that actually rivers are really narrow, less than the width of my cell. So what if I represent rivers as the lines or the edges? And what goes from water goes from node to node. And then for rainfall just accumulates along the length of my line. But it goes down the steepest route from the steepest slope from node to node. We'll call that node to node steepest descent. And then we could have a node-to-node distributed model where it goes from node to node, but it's distributed down all slopes weighted by the relative change in gradient, or the relative gradients. So I ran my solution to the Smith and Brotherton equations for transport of sediment down slopes. And I got 4 different outputs. This is at a low resolution, 128 elements by 512. This is the cell to cell for steepest flow, steepest path of descent. This is for multiple flow direction. So single flow direction, multiple flow direction. Geez, remembered my acronyms. You could say they look rather similar. If we do node to node, you can see that the topography is higher. That's because rainfall only falls on lines or flow only accumulates on the rivers. And naturally, I have less water in my model, so it's slightly less erosive. But here in these little plots, you might start to notice that they're a little bit different. And all I've changed is the flow routing algorithm, not my physical equations. If I increase the resolution, now we've got 512 cells by 2048. The models are starting to diverge. This one is very spiky. Now, of course, these plots are far too small to see properly. So what I did is I will take the big models and we'll blow them up. So this is 512 by 2048 cells. This is single flow direction cell to cell. And you can see the water coming down, but actually I think it looks prettier in elevation. So there were the 2 measures, sediment flux out and the valley wavelength. I want them to be the same and not resolution dependent. Okay, this is single flow direction. node to node. This is the water fluxes, and this is the elevation. Like I said, elevation is higher. We have less erosive power. But what I'm interested in is the valley spacing and the sediment flux out. And we can keep on going. This is cell to cell. It looks pretty similar, I'd say, to this one, single flow direction, but this time it's multiple flow direction. Bring it up. And the last one is my favorite, node to node, multiple flow direction. And we'll put it in elevation. We can even zoom in. This little widget was developed by Bain Sullivan, who now works with VTK, I think. No, not VTK. I forget where he works now. But he develops the people that make ParaView. It's really cool. What I did, rather than looking at cool plots, which I could look at all day, is I plotted sediment flux out of the model and against model resolution. And here is single flow direction, cell to cell, and multiple flow direction, cell to cell, single flow direction, node to node, and multiple flow direction, node to node. The dashed line came from the input of Chris Paula. He said that this line, and I'm afraid after a year, I cannot remember the formula, but at this line, the model should have reached steady state. The formula's in my paper, if you want to go Google it. What we can say, however, about the models, this is sediment flux, and this is time. As we reach a certain resolution, I would expect the models to give the same answer. I think that is reasonable. What I can tell you is that single flow direction cell-to-cell model, I'll zoom in here, you can see that the red line is at 64 on the x-axis, 64 cells. We're going up to 128, 256, and 512. And they're not converging to the same solution. It's also alarmingly jumpy. This is not a very good model. If we do single flow direction node to node, well, I don't really need to zoom in, but you can see it's the same. The models are not converging to give the same solution as I increase resolution. Multiple flow direction cell to cell. This is better, maybe, than this model in single flow direction. It's debatable. I would still say that the black one, and that's the highest resolution, is diverging from the blue one, and that's the second highest resolution. So it's not super great. However, and I did say this was my favorite, the multiple flow direction node-to-node routing algorithm is giving models that tend to overlap. It's better. It's not perfect. Nothing ever is, but it's better. So in this measure, it's best to use multiple flow direction node to node if you're going to do some transport limited landscape evolution modeling. What about the wavelength of the valleys as a function of model resolution? Here are some box whisker plots. Here's my resolutions for the models. This is the single flow direction, cell to cell. This is the single flow direction, node to node. And this is the multiple flow direction, cell to cell. And this is the multiple flow direction, node to node. The mean, well, that would be the median actually. The median wavelength for single flow direction cell to cell model diverges. It gets wider. It also gets wider for the single flow direction for node to node, although it's not bad. And the variance is very large on this last one. When you do multiple flow directions in your landscape evolution model, and I guess I do have to add the caveat that I'm transport limited, then you see that you get this flat line. My wavelength of my valleys is not dependent on the resolution of my digital elevation model. This is very pleasing. This means that it's a good way, let's say, to route water down slopes, assuming that hydraulic gradient is equal to topographic gradient. And so this model becomes my preferred model. And arguably, the model becomes reproducible. And I should say that now that I don't work in academia and I work in a sort of, they call it an EPIC in France, it's a crossover, it's research and industry. And we create software which other companies then sell. And one of these models is called the Dionysus flow. And we cannot have the Dionysus flow give predictions to stratigraphers and sedimentologists of possible places for clastic deposits or marine deposits. That's a function of the input resolution that they choose to use. This makes them a little bit angry because they might get a better, higher resolution LiDAR data or DEM, rerun the model with the same parameters and then get a different answer. That's no good. We need our numerical models to be resolution independent, even if they are detachment limited models using the stream power law. And so I think that we're in a bit of a dangerous spot in landscape evolution modeling, and we need to think about better ways of routing models, routing water downslope. So given that I can't see any of you, I don't know if any of you got that, but that's the end of part 1. Part 2 is kind of more about how I shared all of that. If I click on this link, in Nature in August, just like last month, this paper was published on, well, it's replication, not really reproduction, but it's of a challenge set by 2 French researchers to reproduce or replicate models that you did 10 plus years ago. I'm 100% certain that my models would fail, so I didn't try. But at the bottom of this article is a very nice reproducibility checklist. And so I copied that in my presentation, and I thought I would go through it. The first one makes me smile. This little bar is very narrow. So steps to have reproducible research. Workflows based on point and click interfaces such as Excel are not reproducible. We'll get more into that in a minute, but don't use Microsoft Excel, please. You have to document your codes. Yes, it takes so much time though, so why bother doing that? But it would be a really good thing to do. You need to seed your models. I guess I forgot to tell you that, but I did run multiple models with different seeds to see how reproducible they were when I increased the resolution. Oh, test functions, that's fun. And create master scripts to guide people through your work, or why not Jupyter Notebooks? It keeps on going. It's quite a long checklist. You should archive. GitHub is popular. You could use Bitbucket or GitLab if you want to do that. You need to get used with Git as well. Or you can use even something better, which is permanent archiving like Zenodo for your data or your software. And you can use version controlling, you can package, and this is what I'm going to get into. This might sound like gobbledygook. You need to use Docker or Binder to create virtual environments of your code, of your workflow, of your data analysis. And you can, if you're really good, you can automate it using Travis, but that's really tough actually. Avoid niche libraries and verify it. So what I thought I would do in the remaining time that I'm here is give a sort of flavor of 4 parts. I don't know how accurate I am on this, but I'm going to give it a shot. There might be a live demo. It might be a total disaster. The first one is I want to demonstrate how Excel is not the best and can not be super reproducible. You need to have your regression analysis done in code, please. Then some notebooks. Well, actually, this whole presentation is a notebook, so we'll get to that. Archiving. Well, this is all on a GitHub repo. I'm not going to tell you how to use Git, but that wouldn't be more than the short presentation. And the final thing, though, is I do want to give a little quick show of how Docker works so that we can then understand how Binder works, and people can put their notebooks up on the cloud, and everyone can see what we are all doing. So Excel's not fit for research. even if you're making a bar chart, like this bar chart of mean river width over frequency, it is best that it's enshrined in code. That way, when somebody comes to read it, and I say did it plotting it in 10 bins, later on somebody can come and say those bins are too wide, I want them to be narrower, and you can replot it in 40 bins without having to download the data, install Microsoft Excel, assuming you have a license for Windows, or you can use LibreOffice and do battle with it. I have another example. I wanted to look at the relationship between catchment area and discharge, let's say. So I went to the book by Milliman and Farnsworth. This website is super slow. I don't know why Cambridge is so slow. In this book, they have the data. That's awesome. You can download it. It's an Excel spreadsheet. That made me cry. But we can analyze it in a notebook. If I go back to the notebook, we can look at it. And this is how I find out that Excel is really not fit for research. The first thing you can do in Pandas, it's a library that's great for loading and reading data frames, is you can read in a CSV file. So the first thing I had to do is I had to switch the Excel format to a comma separated variable file. And then I just did a simple describe of the maximum elevation in the data provided by Milliman and Farnsworth for river discharge. And I discovered that there were elevations that had greater than 500. And I'm sorry, but that's not a number. I don't know how to deal with that. I then had a look at the column that had climate T, which is the sort of climate zone, and I discovered that there were typos. STR is subtropical and STR is subtropical. So I'll have to deal with that. In fact, this spreadsheet's a bit of a mess, but cool, the spreadsheet's there, so I can use it. But I had to clean it up, so I'm not a data scientist, so maybe there's better ways of doing this. I wrote little Lambda functions to tidy up all the data to get rid of greater than 500 or less than something else. This is nonsense. These are not numbers for elevation, and to correct typos and just make the column headings a little bit easier to read. Then you can plot the data. You can enshrine it in code. So I can plot water flux versus catchment area for the different climate zones, and we get a nice scatter. Perhaps it's linearly related. And now you can do linear regressions on that. And so that's what I did. I took, of course, I did subtropical, the green ones, and we can get regressions for that. Of course, it's on a log-log plot, much better. So we convert them to log, and we can plot them on a log plot. And now we've got reproducible data analysis on a notebook, locally hosted. You can even get data on that regression, and you can see the R-squared value is 0.2. It's actually not a very good fit, although the p-test says that we're good to go. They are correlated. But this isn't a presentation about how catchment area is correlated with water flux. So that's how we can do data analysis. For example, in the data analysis, I had to install various programs or libraries to do it. This is me using NumPy. This is me using Pandas. This is, at the end, me using StatsMods SM. You need to then, if you're going to be fully reproducible, have these dependencies of which your data analysis or your software is dependent, contained within an environment. And in the world of Python, although it's not just for Python, in the world of R, in the world of Julia, you can use Conda as a package manager. And you create a text file that will list all of the dependencies for your analysis. Mine's cut off. This one's quite large for this presentation. And then you have to create that environment and use Anaconda or Conda. We're using create a Python environment, and it's a little bit involved. But that environment will then sit as a unique body on your computer. You can even do it in Windows. And then you know that if you work in this environment, if anyone works in that environment on their computer, your code, your analysis will run and it will technically be reproducible. But you can take it a step further, and this is where Docker comes in. You could make a tiny little computer, we'll call it, it's not really a computer, but we'll think of it as a computer, that contains only that environment in which you are working, in which your data analysis works, that has all the dependencies upon which your analysis requires. And that's called a Docker container. Whew. If you're all with me, Docker containers, they're little virtual computers. They're actually invented by Frenchmen. They're little virtual computers that do only one process. Your computer, my computer, it runs multiple processes, has a multi-threaded processor. It's doing many things at once. This one's running Zoom, Google, Jupyter, Python, the Python kernel backend. I've got PyCharm running. I've got LibreOffice. A Docker container doesn't do that. It does only one thing. And that one thing could be run a notebook, like I'm running right now. And then that Docker container is defined by a Docker file. And Docker files are actually very simple. So I'm going to put one up here. At its base, it is an operating system. This one is a very simple Linux operating system with Python libraries pre-installed, so it's called Python. So from this base image, we're going to make a little container. We're going to copy locally from my computer some files in Linux. Every file in this directory would be dot to the container, which is the second dot, which is rather neat and cool, but not very easy to understand for the non-initiated. But we can copy everything from the local directory into the Docker file, Then we can install the requirements. In this case, we'll use pip and not conda to get some requirements. That's all the stuff that's required for my script. And then you can run the script upon starting up the Docker container. That's a simple Docker file. This is a Docker file for a notebook. I'll just close that. If I can get a tiny cross. No. We can open this. Oh, I know he's right underneath that guy. So I didn't realize Zoom would get in the way of my screen. But anyway, this is that Docker example that I'm going to go through. It's on my GitHub repository. We'll look at that later. It's essentially the same. We're going to use a Jupyter image, so we don't have to do lots of hard stuff. We're going to copy some files over, an environment, other dependencies, some data. This is on the Pomeroy catchment. It's a comma-separated variable file and a notebook. We have to do some problems with changing the user to do the copying and then changing the user back to the notebook user so that when we open it up, we can use the notebook. And we're going to use conda in a rather convoluted way to install the environment. And I'm also going to use Seaborn, which on conda doesn't really install very well, so we'll use pip. And this is where I'm going to have real fun. We can do a live demo, perhaps, of this. So this is in PyCharm, and it's just an editor, the same Docker file. This is my environment. We've got NumPy in this case, matplotlib, and pandas. And we're also going to install Seaborn. Normally, you would do a Docker build, which I did earlier this morning. We can do a Docker build. That will build the Docker file. It's very fast because I've already built it. It does it in the steps, basically, as the file says. So step one is take the base image. Step two is to change the user. Step three is to do some copying and blah, 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 until step 4 and 5, up until 10 is to do the conda update and the conda install. And we have our little Docker file. And we have made a Docker image. It's like a virtual computer that's turned off. If we do a Docker run of our image, we'll call the run image or the running notebook, That's its name. And what we have to do is expose it on our local host. This is the IP address of your local host of your own machine. It's always the same, 127.0.0.1. And we're going to expose the port. Computers have little doors to them. The door that the Docker is going to send its signal out of is 88888, and so we need to map our port 88888 to that port. If we run that with Docker, it'll be fine, and then I'll just have a look at the log of my Docker file to get the link, and if I click on that link, it'll open up my little notebook. This time, instead of the presentation, which was in localhost on port 8890, that's the port I chose, so it wouldn't interfere with this one. Now we're on the local host, but we're actually in a Docker file. We're in a Docker image. I can demonstrate that to you if I open a terminal in my notebook. You can see that I'm not on my computer. I'm not called Joven. And this is the Docker. For example, if we do ps-aux to see all the processes running, PID number 1 is the container, the notebook. It's running a few other little processes in the background to serve the notebook. But this is the only process, number 1, that somebody from the outside can get access to. And you can then launch your notebook. This is the little notebook. We're exploring how rainfall affects sediment yield and other things. The data comes from a nice little paper by Christine Franke and Claire, I forget her surname, on this little catchment that's in the north of France. And you can see if they're correlated. Is sediment yield correlated to rainfall? I don't know, it's a bit of a mess of data. All of that notebook, that data analysis is unique. It's hosted on a Docker container, and that Docker container can run on anything with Docker. That's cool. That was really hard, and I wouldn't expect somebody that still loves to use Excel to do the data analysis to suddenly write Docker files. So luckily, there's something called Mybinder. Mybinder will turn your GitHub repo into an interactive notebook via Docker. It will expose your notebook on the cloud, and all you have to do is put in the URL of your repository and it will create it. It's obviously a little bit harder than that. This is not this free software, free for you, so you might have to fight it a little bit, but honestly, it's awesome. The people at Jupyter have made something really special, particularly Tim Head, who I think is responsible for repo to Docker, which is what this uses in the back end. And that's where we can say, let's look at this presentation again. This is the reproducible presentation. It's on a GitHub repo, and you can launch the binder. I did this earlier. And it may have crashed, so we'll launch it again. You can see that it's found the image because I've been building it a bunch to make sure it works. And it will launch using repo to Docker, a Docker file of my presentation. And in the presentation, you have the data that I used, the Docker example that I showed you, the notebook, that's a presentation, a README, that creates a nice little README in the GitHub repository, an environment with all the requirements, and 2 other little files that is to do with PyVista, which requires a little bit more than just an environment. And this is where I suffer from doing a live demo, because it's spinning so slowly. The other issue might be because I'm using Zoom at the same time. Well, we could open it for questions. while we're watching the wheel spin. How do I do that?
I will do that right now. That's a great idea. Okay, the chat is now open for questions.
Oops. I'm going to just quit the share. Maybe it will help things out. I can see you all. I'm looking at the list who's listening. Loic, you need to give me a question.
John, I have a question since we're, we also have, well, okay, I'm going to go first and then we'll do this one since it's in that order. I was curious if you could just speculate on the first part of your talk about the possibilities for if you were doing detachment limited erosion. Would all those effects be basically the same, do you think, in terms of resolution effect on valley wavelength and things like that? Or is there some fundamental difference that's going to affect which flow routing scheme performs best?
There's the fundamental difference, unfortunately. It's very disappointing. When you do stream power law, you're basically causing a great concentration, I think. I think Jean Braun's got a good explanation for this that he gave me, but you concentrating flow very heavily. And so even if you distribute your flow, the gradients become so steep that you might only be distributing in the end over a few cells. It still becomes very localized, and you still are resolution dependent. I don't know. I don't know how to overcome it. It's something they're thinking about at IFP, but it's certainly a big problem. My curiosity is now piqued by the work of Philippe Davy, really, and Alan Crave when they use precipitons, and you're trying to be smarter and say that water doesn't just have a hydraulic gradient that is equal to the topographic gradient, and you can allow your precipitons to overcome barriers. Maybe this would be a neat way of having a fast solution to have something that's a bit more distributive than the classic steeper slope of descent within detachment limited models. I think that's about the smartest thing I have to say about that.
Great, thank you. Steffi, do you want to do the next?
Yeah, hey. Yeah, the question is, John, did you restart your presentation? Like, are you planning to continue your presentation, or should we just move to the questions now?
Just move to the questions.
Okay,
I don't know why the binder link is not working. Maybe one or two people are also doing it at the same time, or maybe with Zoom, my internet connection is saturated and it won't bring up the notebook.
Okay, good. So that
Sorry,
maybe just
it's not good. It's bad.
not advertising. The general idea is that you can post questions in the chat, as some people have already done. But if you prefer to ask your questions live, you can also raise your hand, and we can then ask you to unmute yourself, and then you can basically unmute your microphone and ask your questions directly. But for now, I'll start with the first question in the chat, which is by Tobias Hasse. Right, it's a comment and a question. I'm still processing the GitHub Docker bind, lots to learn. My question is about the importance of the model converging before reaching Chris Paola's dotted line.
Yes, that's a nice question. Chris Paola's dotted line. I wish I could find, I'm looking for, I'm not going to find it though. The importance was, Chris Paola's line was a relation between the height of the elevation relative to the uplift, and you want to have the change in height sort of stopping or being, what was it, equal to some number? Gosh, this is so long ago. But the Chris Paola from lab experiments, he came up with this. It might not have even been him, it might have been somebody like Gary Parker, that this was, when you've got constant uplift, there's a certain elevation which is attained, which is balanced by the sediment flux out, and this number is the steady state elevation. And so that steady line I was plotting was the time it should take for that. And so is it important? I don't know, but it was nice that they converged before that dotted line. You'd have to read the article that I published in eSurf last year to get better information. It's a really bad answer. Sorry, Tobias.
So I have a quick follow-up question on this, which I might just drop in between. So when you were comparing your models, you compared the sediment outflux and your wavelength between, the distance between the valleys. But there was this obvious difference in final elevation. You didn't seem to be very bothered by this major difference between the node-to-node and cell-to-cell algorithms.
Yeah.
But isn't this a big issue? So when I have a certain rainfall amount, I keep everything else constant and my final elevation is completely different?
It is, but I have a coefficient in front of the water flux, and so I could just change that to balance it out. The difference is because in the node-to-node model, it is assumed that water only flows down lines. Whether that's right or wrong, I don't know. But the idea that I had in my head was that actually rivers don't collect runoff off an area of landscape that just dribbles off the surface of the earth. It's actually that rivers collect their water from seepage, from base flow, and they collect water into the river, and the river is actually very narrow compared to the landscape. So maybe your river is only a line, and so maybe we should only have lines instead of areas. The other reason I wanted to play with having lines was because one of the reasons that you can have a resolution dependence is because your water flux is a function of area, and the area is a function of the size of your cells. So I thought maybe having just node to node, even if it was steepest over descent, would help, which unfortunately I was wrong on that front. But I'm not too fussed about the change in height between the two models because I have an arbitrary coefficient C in front of it, and I'll just change that.
Okay, thanks. Charlie, do you want to continue or should I just ask the next question?
You just go for it. You're doing great.
The next question is from Thomas van der Linden, and he asked if you verified the model landscapes with reality.
That's what we're trying to do now. That's really hard. That's what we're trying to do. For a game, maybe one day people will see it, I chose a very nice model called Caesar List Flood. It's actually called Hail Caesar. It's been also Hail Caesar. It's been converted from C# into C++, so you can run it on Linux by Declan Wolters. And I've been playing with that and running it on a catchment in Greece. And it runs, of course, on a DEM, and it produces a sediment flux output. And it assumes, it uses the list flood algorithm for modeling or approximating the shallow water equations for the flow of water over the surface, and does other nice things. And you can predict the suspended and the bedload sediment transport out of the model. It obviously is a model that has its own limitations, but what I thought I would do is compare how that compares with my code Phlegm, which doesn't do much fancy at all. And I can say that Phlegm doesn't do well with that reality, but the biggest issue is my model assumes that it's transport limited always, and what we're finding as we try to turn landscape evolution models to real landscapes is the depth to bedrock, the amount of, or the thickness of transportable material that you have on the surface is a big limiting factor on how well your model simulates reality. And this is an input to the model, so it makes it very difficult to compare your models with reality. But it's something for the future. I think there are plenty of other people who do quaternary landscape or even shorter landscape evolution modeling that are looking at this. So, next question.
Okay, so the next question is from Fiona, Fiona Club. Cool talk, John. Love the Jupyter presentation. What do you think the main barriers to reproducible code are?
That it's not valued in academia. Nobody cares. Nobody will pay you to document your code. Nobody will pay you to learn about Docker or Binder. Nobody really cares. I mean, NumPy was published in Nature recently, but I personally, that's because I think Nature's jumping on a bandwagon, and maybe academics will change, maybe. But I think the biggest barrier is that it's hard, it takes time. I mean, if you take the example of a good business like Bon Privé, which is like the French version of, I don't know, it sells stuff, Bon Privé, it sells all sorts of things. So it's kind of like a French version of Amazon, I suppose. It has to run all times, all days. It runs using Kubernetes, which is a sort of network of Dockers that are always running, always scaling. And there's a team of well-paid people that will keep it going always. And these are software engineers. Now, if you demand the same from academics to have code that always works on any system, on any software, and is always reproducible, but you're not going to pay anybody anything to do it, then it's not going to happen. So I think the main barrier is that it has to be valued. Otherwise, it's not that hard to learn. Just have to try.
So that would have been my follow-up question. How about education? I mean, you are not at the university anymore at the moment, but
no, I think another, yeah, you could teach it at undergraduate level. You could. It's not that hard, but it's not that easy. But it could be a course. You could have a course on where everyone works in notebooks, but doesn't just treat it like just another software that they use, like another MATLAB, but they learn actually how it works. But you have to be motivated. There's lots of boring parts, like IP addresses, ports. Yeah, could be education, if you want.
Okay, then I think we just go for the next question. Charlie?
Sure. So let's see. The next question is from Anand Pandey, and the question is, I suppose, Anand, would it potentially be possible for you to unmute? I'm not going to get this right. I apologize for that. I will find you in the participants list.
Hi, it's very nice seeing it. I joined a little late. I'm Anand from India. We're working on like landscape modeling. I saw very nice when you look at the sediment flux. My interest was more on like erosion potential and landscape. So is it possible, suppose I have a complex catchment in which you have multiple channels which are evolving from a different relief zone. So once you have a different relief, it will have a different potential for erosion and thereby different sediment flux. So is it possible to like distinguish their contribution at the mount, let's say a catchment front or something like that?
As it's only as good as the model is. Not with the code that I presented, but certainly with certain numerical codes, you can say, you can try and label in some way your subcatchments and try and track what particles come out from various subcatchments to see what ends up in the main catchment. This is something that Marco van der Wiel, I think, did or talked about doing with Caesar. So it is possible, but it becomes numerically expensive because you start to track individual parcels of sediment as they are transported down the system, and you're needing a code that is probably dealing with water. None of the possibilities, maybe the code Eros does it, but that's a bit more tricky to deal with because Eros is not, as far as I'm aware, open source, and you need a Windows machine to run it.
Thanks.
But okay.
Great, thank you. We have one more here in the chat from Alex Mitchell. Let's say you find a resolution dependence in a model. Is fixing it basically a matter of shopping around for a different model, or are there basically modifications you could make to make that happen for a given code?
I don't know. It depends what's causing the resolution effect. You could try. You could, okay, the code's not just going to go in the bin, of course. One way of looking at it is to say that the code is some sort of abstraction of the real processes at play. This is done with, say, Navier-Stokes. A Navier-Stokes model would be, and I might be wrong, but I think I'm right. They're always resolution dependent because it can't capture everything that's going on within the turbulent system. And so you have to say at some length scale, I'm stopping. I'm good up until this length scale. I'm resolution independent up until this length scale. I cannot capture anything that's smaller than that. And so if you can find some diffusive length scale or characteristic length scale in which your model is limited at, you say anything below this length scale, I can't deal with. That might improve the ability of the model to then be resolution independent. But then it limits what you can apply your model to. So if you're going to say that my cell size has to be limited to a kilometer, then you can't start looking at processes that happen on a river scale. Exactly how you numerically do it, I'm not sure, but it is one avenue that we're looking at IFP Énergie Nouvelle.
Great, thank you so much. So last chance for any questions, either in the chat or from hand raising.
I would have one while we're maybe waiting. So if you get a resolution dependent differences in your sediment outflux, for example, so you say the problem is the routing of the water, but is it also possible that maybe the problem is the equations that we use to describe the landscape processes, that they are not appropriate enough? So then, like, if we would use other equations, then we would have less issues with the resolution dependence?
Yes, if you wanted to solve the shallow water equations, then, and if you solve them properly, I think, on the right sort of mesh, then I think you would not have resolution problems, although they're kind of a simplification of Navier-Stokes, so you might still, but yeah, fundamentally the problems, the problem is with the simplification of the system, which comes back to this sort of the answer before, is that you have to try and find the length scale that you're comfortable with, and you say your model works to, and then it's no longer resolution dependent. But I think I come back to that, if the assumptions behind the model mean that it is just as fundamentally resolution dependent, then that's not good. I'm trying to be diplomatic. Then maybe we should shop for a different model.
Good, thanks.
Great. Well, John, thank you so much. We really appreciate the talk and especially the live demo.
Oh, what a shame. It didn't quite work, didn't quite pull it off. But if you go to the GitHub link that's out there somewhere on the internet, then it might work. Oh, look, haha. For all 61 of you that stayed to the end, finally came up. This is the presentation It's a Jupyter notebook. It's very slow. Here it is. It's the same text. You can run it. I won't run it because I only get 2 gigabytes of memory. But as you can see here, it's on the Google Cloud, GKE, Google Cloud, on a Mybinder. It's the presentation. It's running on the internet. And voila. There you go. I'll stop the share. For a special treat for all of you that stayed, there you go. The live demo did work. It just took about 20 minutes to boot up.
Wonderful. Well, thanks so much. And thanks to all of you for coming. And we'll remind you that next Thursday, we have Jean Braun from the GFZ Potsdam talking about crustal flow over a steady state topography in Tibet. So thanks very much. And we'll see everybody next time. Thanks a lot, John.
Bye-bye.